All right, I had to split this bad boy into two because it was getting very big. So more derivatives, part two. We're going to find the derivative of the square root function. Again, using the definition, and then we're going to come to some sort of a general realization. So there it is. It's the limit as h goes to 0 of square root of x plus h minus square root of x over h. You should be getting pretty familiar with that definition by now. So this is different. Before we were expanding binomials, x plus h to a power. Now we have the square root of x plus h, so there's no expanding that. So the move is to conjugate. So remember the conjugate of the square root of x plus h minus the square root of x is the square root of x plus h plus the square root of x. So we want to multiply the numerator by that in order to simplify it. And we're gonna, we just also have to multiply the denominator by that because otherwise we're not allowed. So that's what we mean by conjugating. So still working within the limit to try to simplify it to where we can just stick 0 in for h. That's what that looks like. So when you conjugate, you'll notice the same kind of thing always happens. The square root of x plus h times the square root of x plus h is x plus h. The outer and the inner terms drop out. So it's plus something minus that same exact thing, right? So those cancel each other out. And then minus the square root of x times the square root of x, which is just x. So that whole numerator now is just going to be x plus h minus x. And then the denominator just is whatever it is and leave it. Don't bother multiplying out the denominator because something's going to factor out. That x and that other x get rid of each other. And then you should, right now you can see something cool is about to happen because we're going to have an h left over in the numerator with an h in the denominator, and that's that. Right, that's why we didn't multiply the h out. It would have been okay to do. It's just now it's gone because we have an h up top and an h in the bottom. So we factor out that h and we get rid of our 0 over 0. Now, if you look at it, you can just say, okay, if I punch in 0 for h, I have solved the problem. So it's just 1 over, right, square root of x plus 0 plus square root of x. All right, so that's the limit. That turns into that. And then the square root of x plus the square root of x is the same thing as 2 times the square root of x. It's just like a plus a is 2a. Okay, so there you have it. A new derivative, 1 over 2 times the square root of x. Again, this isn't, there is a general rule, so don't think, oh, I have to multiply, or I have to memorize this for square roots and cube roots and fourth roots. Nope, there's a way that it works. We need to see the way that it works, at least for one of them. All right, so that goes on the big wall of derivatives. You should maybe start like in your notebook, just like a separate page, a reference page with just all the derivatives we've come up with so far. So the power rule, well, all we really have so far is power rule, constant multiple rule, stuff like that, you know, the sum and difference and stuff. Now we have this one. So all we can really do to verify that this seems right, I mean, it is right, we just showed it by that definition, but let's look at the graphs. So the square root function is a graph, you know, that's the green curve, and then its derivative is that red curve. Notice a couple things right off the bat. Square root functions aren't defined for negative numbers. And its derivative also isn't defined for negative numbers. So that's nice. They share a domain, except for at one crucial spot, and that spot is important. So square root functions also are increasing everywhere. It just goes up and up and up, although pretty slowly. And that means its derivative should be positive everywhere. And if you look at the red graph, it looks like it is. It looks like it has a horizontal asymptote, which should make sense because of what we just said. Square root function starts to level off and increases pretty slowly, so the derivative is pretty small. It's never quite 0, but it is pretty small because the function is not increasing very fast. So here's something we haven't seen. The square root of 0 is 0. So our function is defined there. It's okay. And it even it qualifies as a local minimum there. It looks different, but it is technically the minimum value of the function in that area. But the derivative doesn't do the thing that we expect it to do. It actually hits an asymptote. It hits a vertical asymptote. So it looks like the derivative isn't defined at 0. And if you just look at what the derivative is, 1 over 2 times the square root of x, well, that's got a 0 that's dividing by 0, so it's not defined. So that's why it has that asymptote. So we have a case here that we haven't seen where the function is defined, but the derivative is not. So we have a spot where the function is not differentiable. Most functions can be differentiated anywhere along their curve. So it's instructive just to look at the couple of cases where they can't. There's only a couple of things that can happen, and you should sort of be able to identify them on sight. But I just want you to see that this isn't, math's not wrong. It's just this notion of finding the derivative doesn't always work. Okay, so cases where a function is defined, but it doesn't have a derivative. The absolute value function looks different than other functions because it has a v, right? Because it's v-shaped. And also because it's not as much of like an algebraic rule as something like x squared is. Absolute value means a different depending on if a number is positive or negative. So in particular, we want to look at that spike. We want to look right at x equals 0. We want to look at that corner and see, spoiler, so the derivative doesn't exist there, and we want to show why that would be, and that it jives with our definition. So we try it. We try using our limit definition of the derivative. It's, instead of saying f prime of x, we're going to say just f prime of 0. So we do want to have a derivative kind of for absolute value, but in particular we want to look where we want to look. So f prime of 0 is the limit as h goes to 0 of absolute value of 0 plus h, right, minus absolute value of 0 over h. So stuff goes away, and that's what we're left with. We actually saw this same exact thing, this same exact limit, when we talked about places where the limit does not exist. So if this limit doesn't exist, which it doesn't, then the derivative doesn't exist there because, again, the derivative is just this specific type of limit. So we saw that when we looked at a curve that was one thing coming from the left and some other thing coming from the right. That's exactly what this is. So from the left, absolute value of h over h is always -1. So it'd just be like 5 over -5. From the right, absolute value of h over h is just 1, because for a positive number, that's just like 5 over 5. So, right, we have a different limit coming from one way rather than the other. The one-sided limits are okay, but the actual global, remember, if we say as h goes to 0, it has to come from both ways, and it has to agree there. So it doesn't. So this limit we're looking at does not exist. So therefore, the derivative does not exist. The function is fine, right? The f of 0 is just 0, but f prime of 0 does not exist, and we just say that the function is not differentiable there. So in general, when you see a corner or a spike or a kink or anything like that in a curve, there's not going to be a derivative there. So you should just be able to look at curves and be like, it's not going to work there. Just picture that tangent line moving along a curve in that nice smooth way. You can't really imagine it happening right there. Remember, a tangent line glues itself to a curve and kind of approximates it. But if you think about trying to stick a tangent line onto that spike, no matter how much you zoomed in, it would still look like, right? It wouldn't look like the tangent line was sticking to the curve. And you can almost say it's not even really curved there. It's angular or sharp. So that'll bear out when you do the math, but now you just know what to look for. So here's my metaphor. At that spike in the curve, the function all of a sudden switches from just plugging along at a rate of -1 to abruptly switching to plugging along at a rate of 1. So this would be like bouncing. Like, okay, if you drop a ball to the ground, it has one velocity. It hits the ground, bounces back up with a completely different velocity because it's going a different direction. So at that very moment that it bounced, you can't really define the ball's velocity. You can on either side of that moment just fine. It'd be like if you were going 10 miles an hour in your car and all of a sudden you switch in reverse and started going 10 miles an hour in reverse. Well, you'd destroy your car. But theoretically, if you didn't, then at that very moment where you switched or bounced or whatever, then you couldn't really define a speed if we're thinking of a derivative as velocity. So back to the example we just saw, the function just goes to 0 and stops, but the derivative shoots off to infinity at a vertical asymptote. So this is different. If you were to zoom in on the square root function near the origin, you would see that right at 0.01, it's increasing incredibly fast, and in fact, it looks like the curve is vertical. You can't really see it in that picture, but just picture zooming into that green curve on the origin, the curve is practically vertical. It's not quite, because then it wouldn't be a function, but it practically is. And so the tangent line comes along, and right as it hits the origin, you would technically have a vertical tangent line. So that's a different thing than just not having a tangent line at all. But if we think about instantaneous rate of change as the slope of the tangent line, vertical lines don't have slope. Remember, that's when we said slope is undefined. The concept does not apply. So if you see a kink or spike, or if you see like a real flat spot in a function, like the cube root of x does that as well, where it looks like it becomes vertical for a second. It doesn't really become vertical, but it does become not differentiable. You wouldn't say that f prime is infinity or something, because vertical lines don't have slope infinity. They just don't have slope at all. So we can get derivatives for things like absolute value if we just ignore the problem spots. So just redefine the absolute value as this. Okay, so all this is saying is if x is a negative number, if x is less than 0, just flip the sign, right? So if x is -4, just flip the sign to be 4. If x is a positive number, or 0, so if x is greater than or equal to 0, then just keep it. Then x is just x. So this g of x thing is just a different way of defining the absolute value function. But you see what I'm saying? It's the exact same thing. It's just a little more mathematical way of looking at it. So now when we compute the derivative, we just ignore 0 because we know it's not differentiable there. But everywhere else, okay, the derivative of negative x is -1, and the derivative of x is 1. So it's almost like we take it, we define it as a piecewise defined functions, and then we differentiate it in pieces. And we had to take off the little greater than or equal to on the x and 0, because now we've made it so that, hey, look, g prime of 0 doesn't have any definition at all. It's just if x is strictly negative, it's -1. If x is strictly positive, it's 1. And we don't even have to say it doesn't exist for 0 because we just don't see it there. So that's really the derivative of the absolute value function. It's a weird one. It probably won't come up again. But if you had to do it, that's how you do it. We're going to kind of, be smarter than the math now. And some of you may already know this rule, and maybe you picked up on it. So if we have the derivative of square root of x is 1 over 2 times the square root of x, remember the square root of x is the same as x to the 1/2, right? So 1 over 2 times the square root of x is the same thing as 1 over 2 times x to the 1/2. And if you have an x to the 1/2 in the denominator, that's the same thing as x to the negative 1/2. So 1/2 x to the negative 1/2 is just the way you'd write 1 over 2 times the square root of x using fractional exponents rather than radical notation. All right, so we've discovered that, okay, the square root of x is x to the 1/2, so the derivative of x to the 1/2 is 1/2 x to the negative 1/2. You see what I'm saying? You see it? That's the power rule. That's the same rule. The 1/2 hops down out front. 1/2 minus 1 is negative 1/2. Right? So, you know, I'm not trying to hide things from you. I wanted you to see that this was right without really proving it, because it's hard. But what we're saying now is, oh, look, it seems like the power rule worked for x to the 1/2. And now we'll just spill the beans and say the power rule also works for fractional exponents. Okay, and it works the same exact way. You don't need to memorize a new rule. You just have to be careful because you're still always subtracting 1. So the different thing here is that that exponent went from positive to negative because 1/2 minus 1 is negative 1/2, but that's fine. You just do the same thing every time. Okay, so same exact theorem. Now we've just expanded our consciousness and say, okay, the power rule works the same exact way for not just positive integers, but positive rational numbers. And an integer is technically a rational number, so this is just the expanded version of that. So it works for fractions as well. We're just working with fractions instead of whole numbers. So for example, if I asked you for the derivative of the cube root of x, here's what you would not do. Memorize a bunch of different derivative rules for cube roots and fourth roots and next to the 7/2 or whatever else, right? Don't do that. Just be good at converting radicals to fractional exponents. You have to know how to do that, right? Because if I give you the 7th root of x and you don't know how to do that, then how are you going to possibly get the derivative of it? So that the cube root of x is the same exact thing as x to the 1/3. So the 1/3 comes down, and then you subtract 1 from the exponent. 1/3 minus 1 is 1/3 minus 3/3, which is negative 2/3. So there it is. That's how you do the derivative of something like a cube root. Switch it to an exponent, just use the power rule. It's 1/3 x to the negative 2/3. If you want, you could switch it back to looking like this, but I don't encourage it. That's the same thing. I just put it back the way we found it, but you don't have to. I would encourage you just to leave it as 1/3 x to the negative 2/3, because A, it's easier for me to grade, and B, it's easier for you just to leave it like that, because what does it matter to you? If you can switch it one way, you can switch it the other way. Just looking at the graphs, just so you kind of believe me. The red thing is the cube root function, so it kind of looks like, well, it looks like a sideways cubic because it is. And then the purplish thing is its derivative. So notice at 0, the function is defined. The cube root of 0 is 0. But if you look at the derivative, that's one reason to put it back the way we found it is if you put 0 into the derivative, you're dividing by 0. No good. So that's why the derivative has an asymptote. So the function just hits 0 and keeps going, but the derivative hits 0 and has a vertical asymptote and shoots off to infinity. And the reason it does that is because of a vertical tangent line. If you look near the origin on that red curve, it looks vertical. It isn't quite, but the tangent line kind of is. So we can't say that it has slope, so it doesn't have a derivative there. So that's another instance of a function not being differentiable, being defined but not having a derivative there. So here's me saying it officially. You can leave your answer like 1/3 x to the negative 2/3. And in fact, I'll go farther and say I'd rather you did. It's just simpler for me. And I mean, the more little algebra stuff you do, the more opportunities there are for you to make a mistake. So I know we always have the urge to simplify in a math class. It's not a bad urge, but when we're doing these derivatives, that's simplified. Putting it back in radical notation doesn't really simplify it. It just makes it look different. So I'm telling you to just leave it like that. That way everybody's looking at the same thing. Okay, one more. We're going to find the derivative of 1 over x the old-fashioned way by using the definition of the derivative. Again, then we're going to take a step back and be like, wait, you know, what's happening in general with this type of thing. So we're just going through all your basic like algebraic non-trig type of subfunctions. So punch it in. This one takes a little bit of a doing to clean up. There it is. It's the limit of 1 over x plus h minus 1 over x over h. You had one on the first quiz kind of like this. We're going to take the least common multiple of those denominators and multiply everything by it. So if you think about the least common multiple of x plus h and x, that's just x times x plus h, right? That's the LCM right there. So if we multiply the numerator by that, we'll clear all those fractions, and then we just have to multiply the denominator by that as well. So we're going to go inside that limit and multiply by x times x plus h over x times x plus h. Looks a little ugly, but acknowledge that it's going to work. If you multiply that first term in the numerator by x times x plus h, the x plus h cancels out, so all you have is an x. That second term, the x cancels out, so all you have is an x plus h, and we've gotten rid of all of our compound fractions. We don't have any more compound fractions. The denominator just is what it is, and if we've played our cards right, something's going to cancel out from that in a second anyways. Okay, so that's what that looks like, right? The first fraction in the numerator simplifies, the second fraction in the numerator simplifies. We have x minus x plus h. The parentheses are important there. Leave the denominator alone. Just distribute that negative sign. Something cancels out. Whenever something starts canceling out, you think, okay, I think I'm going in the right direction. So we have negative h over hx times x plus h. Boom. Some h's cancel out. We know we're going the right way. Divide everything by h. You get negative 1 over x times x plus h. And now we can just set h equal to 0 and actually evaluate the limit. So when h is 0, this is just negative 1 over x times x, or negative 1 over x squared. Okay, so that goes in the big book of derivatives. The derivative of 1 over x is negative 1 over x squared. So let's compare the graphs of 1 over x and its derivative. 1 over x is the red curve. Notice that it's decreasing everywhere and that it has no mins or maxes. So that means that f prime is negative everywhere. If you look at negative 1 over x squared, that's always going to be a negative number. And it's never 0. And then 1 over x has a big asymptote right in the middle of it, which we've seen that means that its derivative does as well, because if the function shoots up or down, then the derivative is going to do that as well. Focusing on the bigger picture again, notice that negative 1 over x squared is the same thing as negative x to the negative 2. And also that 1 over x is the same thing as x to the negative 1. So we have that the derivative of x to the negative 1 is negative 1 times x to the negative 2, which suggests to us that the power rule is still working, actually. And it is. So reveal, the power rule just works for any exponent, no matter what, even negative exponents. So there it is. for any real number n. It could be negative, fractional, it could be an irrational number even. The power rule just works. So the important thing to remember is that you're always going down by 1. So if the exponent's negative, if it's like x to the negative 1, then that goes down to negative 2. It doesn't ever go back up. So you're always subtracting 1 from the exponent no matter what it is, which is great because it just works the same way no matter what. So if I give you 1 over x cubed, you're going to just convert that into a negative exponent. Right? You don't need a different rule. You just need to be good at converting things into exponential notation. So that's x to the negative 3, which is negative 3x, and the derivative of that is negative 3x to the negative 4. So the negative 3 always goes down to a negative 4. You can change that back into negative 3 over x to the 4th if you want. Again, you don't have to, and it's probably better just to leave it as negative 3 times x to the negative 4. That is perfectly fine. All right, so that's about the ugliest thing that we can take the derivative of so far. But believe it or not, we can do that only using algebra and the power rule. We have something called the quotient rule later we can use on it, but I wouldn't. It's easier just to be good at algebra. So we just have to be able to convert everything to exponents and then know all of our exponent rules. So, okay, we want the derivative of 2 times the square root of x plus the cube root of x to the 7th minus x to the pi. Yes, pi is an acceptable exponent. Exponents can be irrational. All that over x squared. So the move here is to split this up into 3 separate fractions. So you can take 3 separate fractions that all have the same denominator and combine them into 1. So we can take this fraction that has 1 denominator and split it up into 3 separate terms. So just verify to yourself that that works because it works backwards, right? We could go from that second step back to that first step because they all have a common denominator. Now take all that radical looking stuff and write it as a fractional exponent. Sometimes it'll just be given to you as a fractional exponent, sometimes not. So the square root of x is the same as x to the 1/2. So refamiliarize yourself with these rules if you have to. The cube root of x to the 7th is the same as x to the 7/3. So that's the general rule. The radical goes in the denominator, the exponent goes in the numerator. And then x to the pi is just x to the pi. There's not a whole lot we can do with that. So now we need, I guess, what we called the quotient rule for exponents. If you have x to the n over x to the m, that's the same as x to the n minus m. So you subtract the exponents. 1/2 minus 2 is 1/2 minus 4/2, which is negative 3/2. 7/3 minus 2 is 7/3 minus 6/3. So that's 1/3. I kind of skipped the common denominator stuff there. You can do that. Pi minus 2 is literally just pi minus 2, right? That's just what it is. So the point of splitting it up is that we can just do all these derivatives separately now with the sum rule. And also, you know, we could use the exponent rules just to make everything look like this. So this is what I call a polynomial type function. That's not a real math term. It's just something I made up, so don't say it anywhere else. But it's not a polynomial, but I call it polynomial type because it's just a bunch of coefficients times x to powers. Since the powers aren't positive integers, it's not a polynomial. But if we just say, okay, the powers are whatever, it looks like a polynomial. So it's what, again, only I call a polynomial type function. And we can take the derivative of any function that looks like this just with what we have so far. So the derivative of x to the negative 3/2 is negative 3/2 times x to the negative 5/2. So we're doing a little mental arithmetic. Negative 3/2 minus 2/2 is negative 5/2. And the coefficients just come along for the ride. So the 2 comes with. The derivative of x to the 1/3 is 1/3 x to the negative 2/3. We already saw that one. And the derivative of x to the pi minus 2 is pi minus 2 x to the pi minus 3. And all that's left to do is clean up a little bit. So, you know, we talk about simplification. There's no reason not to do 2 times negative 3/2. That's negative 3 because the 2's cancel out. And that's it. That's all you can really do. And then I would just leave it like that. There's no reason to take x to the negative 5/2 and x to the negative 2/3 and write them any other way. They're just fine as fractional negative exponents. There's nothing wrong with that. One more example, because I really want you to be comfortable doing derivatives like this way, rather than use anything more advanced like a quotient rule or something. It's better just to be fluent in your algebra and just make everything you can look like a coefficient times x to a power, because then the actual calculus is super easy. So the square root of x to the 5th is the same thing as x to the 5/2. If you forgot why that is, I can explain it, but go back and review your exponent rules. So that's the same thing as 2 over x to the 5/2, right? And then we can write that with negative exponents. That's the same thing as 2 times x to the negative 5/2. And then 3 over x to the 8th is the same thing as 3 times x to the negative 8, right? It's 3 times 1 over x to the 8, which is the same thing. So just convince yourself that works. Now, those are the same thing, right? We haven't done any derivatives yet. We haven't done any calculus yet. We're just rewriting. So here's the calculus. Power comes out front. Negative 5/2 minus 1 is negative 7/2. Right, and then the negative 8 comes out front. Negative 8 minus 1 is negative 9. And then there's no reason not to clean that up. So the 2 and the negative 5/2 give you a negative 5. The negative 3 times the negative 8 give you a 24, x to the negative 9th. And then just leave it like that. So that's the derivative. There's no reason to rewrite it, and there's no reason to do that any sort of fancy or more complicated way.